Hello and welcome back to Calculus, the series where we explore derivatives. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Now, since we have looked at the application of derivatives, mostly finding the tangent, minimums, maximums, and points of inflection, we can continue to work with them under a greater umbrella. Instead of casual linear, quadratic, or in general polynomial functions, we can start including trigonometric, logarithmic, and exponential functions. And today, I'd like to begin this video with the Euler's number, often denoted with a lowercase e. It's a very important concept in calculus, much like how pi is extremely important in trigonometry. The Euler's number e is irrational, meaning it cannot be expressed as a fraction, just like pi, and its value is approximately 2.71828 and so on, never ending. I do have a separate video that goes in detail about how the Euler's number is formulated. However, just as a reminder, getting to the Euler's number requires the use of limits. It's the limit as n approaches infinity of 1 plus 1 over n to the power of n. And the value we approach would be the Euler's number. It represents the maximum exponential growth, and it's also why this number is extremely important in finance. If you have ever done compound interest, you can see probably that this part of the formula looks extremely similar, and that's exactly where the Euler's number comes from. On the other hand, one may ask, why is the Euler's number so special in calculus? Well, this is because of the exponential function e to the power of x. To see why it's special, let's first take a look at basic exponential functions. Let's say we take 2 to the power of x. And now we'll immediately visualize this on the graph. And now, let's say we pick any point on the graph and we're asked to evaluate the gradient at this point. Well, funny enough, the gradient at this point is just going to be 2 to the power of x at that point and multiplied by a certain constant. And I can tell you immediately that constant is 0.693147 and so on. Now let's say we are given another exponential function and it's going to be 3 to the power of x. Now, let's say we pick a point on 3 to the power of x and we're asked to evaluate the gradient once again. It might not surprise you, but the gradient is simply going to be 3 to the power of x, where x corresponds to the value at which we're evaluating the gradient, and multiplied by a constant. And that constant is going to be equal to 1.0986 and so on. Well, what I can tell you is these two constants here are not random numbers. They are the natural logarithm of the base. If you're wondering what the natural log is, it is simply the logarithm with base e. We can simplify this notation by writing ln, which denotes the natural logarithm. It's much like writing log base 10 as just log, where we omit the 10 in the base. Well, and this little graphical analysis here is where the formula comes from. The formula for derivatives of exponential functions in the form of a to the power of x. Well, like you already noticed, the derivative is going to be a to the power of x. and of course multiplied by some constant, which in the general form would be ln of our base a, where a is just a number. In the case of e to the power of x, it's no exception. We still get the same e to the power of x, and then the ln of e. The only thing you should notice here is that ln of e is actually just 1. We know from the logarithmic properties, if you have log a of a, meaning the base and the argument are the same, you always get 1. And this is what happens here with the ln e. This is why e to the power of x is so special, because in general, its derivative does not change. The derivative of e to the power of x will always remain e to the power of x. Well, and logically, next up, I have to explain to you the derivatives of logarithmic functions. If we have a function f of x in the form of log ax, then its derivative is going to be 1 over x times ln of a. However, before I show you why exactly this is true, I would like to discuss the derivative of another important function. And you might have guessed it, it's going to be the natural log of x. Its derivative is simple enough, it's just 1 over x. And here I'd like to show you why exactly this is true. We begin by stating that our function is y equals to ln of x. Well, if you know something about functions, the natural logarithm ln x is the inverse of the exponential function e to the power of x, meaning y equals to ln x, which means e to the power of y is equal to x. These two functions are the same, I just rewrote them differently. One's in terms of y, and the other is in terms of x. And now from this, we can use something called the implicit differentiation, where we differentiate both sides of the equation. Don't worry, this topic will be covered in the future. For now, I will simply use it to show you the derivative. You would agree, doing the same thing to both sides of an equation doesn't change anything. So now we differentiate both sides. On the left-hand side, I can tell you that this is going to be equal to e to the power of y times dy dx. And while on the right-hand side, you already know the derivative of x is simply 1. Now we can substitute x back into the equation, because in the beginning we said e to the power of y is equal to x. That means, instead of e to the power of y, I write x. And then finally, I divide x from both sides, and what we get is dy dx equals to 1 over x. That means the derivative of y is equal to 1 over x, and y was originally equal to ln x. Now that this fact has been proven, I can show you the other proof about the derivative of basic logarithmic functions. Well, step number 1 would be to rewrite log ax. And actually here we can use the change of base. And our desired base would be e, meaning I want to rewrite this logarithm into a natural logarithm. So using the change of base formula, what I get is ln of x divided by ln of a. And well, now we can differentiate this equation on both sides. On the right hand side and the bottom, we have ln a. This is simply a constant. It means I can pull it out into the front. And now we know from the previous proof that the derivative of ln x is simply 1 over x. And from this fact, we arrive to the final answer. And this here concludes the proofs for the both derivatives of logarithmic functions. Now that we have shown all of this, it's finally time to move on to trigonometric functions. And I'd like to begin this with the graph of the function sine x. Well, nothing special about this. It's a repeating curve with the boundaries 1 and -1, which is the range of most trig functions, or the most basic two, sine and cosine. We spoke in the last video and the previous one about local maximums and minimums of a function. And we know it happens when the derivative of that function is equated to 0. Well, here, on this part of the sine graph, we have one maximum point right here and one minimum point right there. This tells us that the derivative function at these 2 points is going to be equal to 0. Funny enough, from these 2 points, we can actually formulate another function. I would also like you to notice that this green graph in this domain has 3 maximum and minimum points. One is right here in the beginning, one right here in the middle, and one right here at the end. 2 maximums and 1 minimum. And you can see that in the sine function at these points, they are equal to, that's right, 0. Well, this green function right here might look familiar, and you'd be right, because it is the cosine function. From purely graphical analysis, the conclusion that we came to is the derivative of sine of x is going to be equal to cosine of x. And then further down, the derivative of cosine of x is going to be equal to negative sine of x. And logically from that, the derivative of negative cosine of x is negative sine of x is going to be negative cosine of x. And finally, the derivative of negative cosine of x is going to be positive sine of x. And this cycle of 4 will repeat forever. There is one more important derivative that you should well remember, and that would be the derivative of tan x. And I will tell you immediately that this is going to be equal to 1 over cosine squared of x. Well, written in other words, we know that the reciprocal function is going to be the secant squared of x. If you want to see why this derivative is true, you can rewrite tan x as sine over cosine, and then use the quotient rule for differentiation. And you will see the answer you arrived at is 1 over cosine squared x, which is the same as secant squared of x. You can try this on your own as a little challenge. However, this of course is not all of it. There are more derivatives that are important and would be good to remember. However, I cannot cover them all, so we will learn them along the way when we meet them. For now, today we have looked at all the theory possible, and in the next video I would like to show you how all the differentiation rules can be applied to trigonometric, logarithmic, and of course exponential functions. So I hope to see you there, and have a nice day. Bye!